So, hi everyone. This is my attempt to get us through the material we should be covering today in Lecture 19. So let's see where we're going to start. If we were in class, I would have passed out Wintergreen Lifesavers for everybody and asked you to do an experiment at home. And that experiment is to go in a very dark room, either situate yourself in front of a mirror in that very dark room or in front of a friend, then put the lifesavers, and it has to be wintergreen. Put the lifesavers in your mouth and crunch it with your mouth open, and either watch your friend do it or look at yourself in the mirror. It should be pretty neat, so you should see something. Failing that, you can also check out this little YouTube video. So that's going to be our introduction to potential. And we're going to find our definition for potential by carrying on with our analogy to gravity that we use to find electric field and electric potential energy. Let's do a recap first. In our recap, we know that gravitational force or weight is mass times the gravitational field. It has units of newtons. Mass is our important quantity here. For electric force, the electric force is the charge times the electric field in newtons. Charge is our important quantity here. So we have forces as a result of the fields. The fields themselves can be thought of the force per unit quantity, if you wish. So force per unit mass is your gravitational field. Force per unit charge is your electric field. And these fields are the agent of the forces. These fields tell the charge or the mass what force to feel. Something very important is that these are both vector quantities. So we'll write vectors there on the side. So forces are one way to describe the behavior of objects. Energy is another way. So let's start talking about energy. So here's a new slide. I've got a recap of our force and our field up here. Remember that force and field are vectors. So why don't we even go ahead and write that in? So these two are vectors. Means every time you answer a question about force or field, you're including the direction. These two are vectors. We also discussed potential energy. Potential energy is a scalar quantity. When we found our electric potential energy, we started off by remembering our gravitational potential energy, which was m times g times y. Y was your height above some reference point. That was measured in joules. And our electric potential energy, we figured out was, U electric equals Q times E times S, where S is your distance from ground reference point, which we chose to be the negative plate. That's measured in joules. So the next step we go to, so there's our energy, that's a scalar. For our potential energy, the M is important. For our for gravitational potential energy, M is important. Electric potential energy, Q is important. So just like field was force per unit quantity, we're going to define a new type of quantity called potential. So field is force per quantity. Potential is going to be energy per unit quantity. So in terms of gravity, the gravitational potential is the gravitational potential energy divided by the mass. So divide both sides by m, we're left with g times y. This is not something you would have studied in physics 1020 or 1050, but this is something that astronomers use quite a bit. So we'll put astronomy under here. Electric potential, that's way more useful to us. Electric potential is going to be our electric potential energy divided by our charge Q. Electric potential has a symbol of V. It's electric potential energy divided by the charge Q. So when we divide both sides by Q, we get E times S. E times S. Because potential is an energy divided by a quantity, potential is also a scalar. So both of these quantities are scalars. So make sure when you're doing your problems, you remember which is a vector and which is a scalar. So what potential tells us, what field tells us is if we place a mass or a charge in their respective field, they'll feel a certain force. What potential tells us is if we place a mass or a charge in its perspective potential, it will have a potential energy. So if I put charge Q in an area with potential V, it will have energy U. So if V is U over Q, then it means that U is equal to Q times V. So those two statements are equivalent. Some other things we'll point out is that the units of potential are volts, and volts have a symbol of V. So there's another thing to be careful of. The symbol and the unit actually are both a V, where a volt is a joule divided by a coulomb. Okay, so I think that's our definition of potential all done. Let's find our expression for potential around a point charge. To find our expression for potential around a point charge, let's use the same method that we used when we found our expression for electric field around a point charge. So we'll do the same sort of analysis. Hopefully you kind of remember this one. So we have some charge Q. So this is our little point charge Q. Point P is some empty point in space. So some point in space, completely empty. Nothing at all there. And it's near to our source charge. So this point charge Q is our source charge. Just like it made an electric field, it also makes an electric potential. Oh, that was one last thing I forgot to mention. Let's go back to that slide for a second. Electric potential, V, it has a bunch of different names. Sometimes it's called electric potential, sometimes it's just potential, sometimes it's potential difference, sometimes electric potential difference, and sometimes it's just voltage. The different people you talk to and the different books you look at will all have different words. Primarily, I'm going to be saying potential, but they all mean the same thing. Okay, now we'll come back to our finding the equation for potential. So point P is near some charge. This charge makes electric field. It also makes potential. So our point charge Q is our source charge. And as a source charge, it makes the potential. And we're trying to find the expression for that potential. So what we do is we place a little test charge at our point P so that it's close to our charge Q. So here's our little test charge. I'm going to call that Q primed. It's a distance r away from our source charge Q. And we ask, what is the electric potential energy? So we know that electric potential energy between 2 point charges is UE equals K times one charge, our source charge, times the other charge, our test charge, divided by the distance between them. Okay, so there's our electric potential energy. For our next step is we take away our test charge. Now we're back to just plain old point P and nothing is there anymore at this distance r from our source charge. And we remember that electric potential is the potential energy divided by the test charge. So it's energy per unit charge. So V is equal to U divided by the charge. So this little charge here will have a potential energy given by this expression. The potential here then is the energy divided by that charge. If we divide Q times Q primed over R divided by Q primed, we're left with KQ over R. So this is the electric potential at some distance r from our source charge Q, or our point charge Q. One last thing we'll talk about is what happens if we are infinitely far away. If this point P is very far away, and I think this is important enough to write down, if P is far away, then R approaches infinity. So our potential, if R approaches infinity, is K times Q over infinity. That goes to 0. So our potential, very far away, is going to be 0, and this becomes a reference point for us. We know that potentials are going to be 0 when we're very far away from a charge. Okay, next thing we'll look at is the relationship between some of the different quantities. So I think this might be a nice reference slide for you. All of our equations for point charges, they look kind of the same, but they're definitely not the same. So electric force and electric potential, those are interactions between two charges, so they have the two charges in them. Electric field and electric potential, they're made by a source charge. They're just made by one charge, so they only have one charge in them. Forces and fields are vectors, so they're written as vectors. Potential energy and potential, they're scalars, so they don't have direction. So this might be a nice reference slide for you. We do know some of the relationships between these quantities. We know the relationship between electric force and electric field. So to go back and forth between these two, we know that F is equal to Q times E, and E is equal to F over Q. We know our relationship between energy and potential because we did that on our first slide here. Electric potential energy is charge times potential, or potential is electric potential energy per unit charge. We also know the relationship between force and potential energy, so we know how to go back and forth between these two. Our force is negative the derivative of potential, so force is negative of the change in potential, or potential energy is negative the integral of force over distance, and that came from our expression of work. So the last identity, the last relationship we'd like to nail down is what's the relationship between electric field and electric potential. That's going to be something we're working on in this chapter.